Welcome to 7 in Physics. Today we're going to solve a question involving kinematics, dynamics, and conservation of momentum. I hope you enjoy. So the part A of this question asks for state the principle of conservation of momentum. Instead of giving the answer directly, I will do some mathematics to explain what conservation of momentum means and when we can apply conservation of momentum in physics. So the first concept we will need to understand what principle of conservation of momentum means is the concept of momentum. Momentum is a vectorial quantity, implies it has direction, and the formula for momentum is equals to mass times velocity. When I draw these arrows here, what I'm trying to say or to emphasize is that both velocity and momentums are vectors. This will be very important because the mathematics of momentum will always consider the direction of the vector. So the mathematics can have some changes depending on if the direction is pointing in one direction or another direction. So it's very important to keep this in mind. The majority of the mistakes students have in collision problems are related to the vectorial nature of momentum. Okay, so we know what momentum is now, and then we will read the principle of conservation of momentum. Formally, it says that the total momentum of an isolated system of objects remain constant. And I wrote two words there in red. The first word is the word system. And when I say system in this context, I'm saying that system is a set of objects. So we're talking about a group of objects which are having an interaction, are having a collision, are interacting with each other and applying forces to each other. Okay? So the momentum and the conservation of momentum physics are useful to understand and analyze systems on which objects are applying forces to each other, for example, in collisions. And the second word, which is important here, is the word isolated. And when I say isolated, I try to say that only the forces related to the interaction are going to be important. We will not consider any other force but the forces related to the interaction. Okay? So when I say system and I say isolate, you know already what the meaning of these words in this context. Okay? So now we will use some other concepts and some mathematics to verify that this principle of conservation of momentum is true. We will express this principle of conservation of momentum using mathematics. To do that, we will use some basic physics concepts. The first concept we're going to use is the link between momentum and force. And this link can be seen in the Newton's second law. The Newton's second law established that the force is the rate of change of momentum respect to time, as you see there. So we have a link between force and momentum. Easy. And the second concept we're going to use is the Newton's third law, which is the famous action and reaction law that establishes that when two objects are having an interaction, and again, it makes sense with the system concept we did before, when two objects in a system are having an interaction and applies forces to each other, the force that, for example, object A is applying on object B, which in this case is this red, will be equal in magnitude but opposite in direction to the force that B is applying on A, which is here represented by this arrow. So to make it simple, what we write is that the forces will be equal in magnitude but opposite in direction. So the forces of two objects having an interaction, a collision, will be equal in magnitude and opposite in direction. So using these two concepts and considering this delta t to be the contact time, which means is the time that the interaction will last, so will be the same for both objects, we will do mathematics to verify again that this principle is true. So let's do it. We will start from the third Newton's law, which is this expression here. Okay? Forces are equals in magnitude, opposite in direction. and we will translate each force as the second Newton's law means rate of change in momentum with respect to time, which is this second expression here. As we said before, delta t is the contact time. So it's the time that the interaction will last. And this time is the same for both objects. So I can cancel this delta t. I can simplify this delta t using basic algebra. And then the equation will become only in terms of delta momentum, of delta p. So the equation will become this. Please follow the colors. So delta pb will be the momentum of B after the collision minus the momentum of B before the collision. This is the red part, and something similar will happen in the blue part at the right with the momentum of the object A before and after. But something very important to mention here is this negative sign here. This negative sign is coming from the third Newton's law, and it's a very important negative sign. You will see why. So I will write now my momentum as mass and velocity. There you are. Momentum before and after for both objects. This small symbol here means after the collision. So we have momentum before and momentum after for A and B. Please follow the colors. Everything in red is for B, everything in blue is for A. And then I will operate this minus with my bracket. And then the signs will change, and I will regroup the equation, and the equation will be like that. What I did there was I wrote terms including velocity after the collision are written at the left of the equation, so are written in this side of the equation, and terms including velocity before the collision are written at the right of the equation, so are written right here. So if we analyze this equation, we're seeing that at the left we have momentum before, at the right we have momentum after. I'm using the word total to emphasize I'm adding momentum before and after, and we can see that the total momentum before the collision is equal to the total momentum after the collision, which means the momentum is conserved. So this small piece of mathematics verifies that this is true. Okay? Of course, when they ask you for conservation of momentum, you will not answer with all this mathematics, but it's useful to understand how it works because you will use fraction of this mathematics later on. So let's solve the question formally. State the principle of conservation of momentum, and we will only say in an isolated system, which means no external forces are acting, no other force but interaction forces are acting, the total momentum is conserved. 2 parts, 2 marks. Part B of the question. Please stop the video now and read the part B of the question. Okay, so as you saw, in this part B, they are talking about a pellet hitting a clay block. So we're having a collision, and then both objects are moving together as one object on top of a ramp. So we will do some physics related to these two situations, means the collision between the pellet and the clay and the motion of both together on top of this surface. Before going to the next slide, I want to say something here. There is some data given, and something important in this data is that the mass values are given in grams. And it's a very common mistake of students that they forget to do the conversions. So please convert your grams into kilograms. I wrote there in red and blue the values, and I am doing that because it's very, very important. It's very, very common that students forget to do that, and then the results don't work out. Okay, so let's go now and solve the question B1. Then say, show that the initial speed of the clay block after the air rifle pellet strikes is 4.8 meters per second. So, in this question, we are dealing with an inelastic collision. The physics of this question implies the collision itself. We're going to work on the collision moment itself. And we say the collision is inelastic because both objects, means the pellet and the clay, will move together after the collision. So we're going to do now physics for collisions. And we remember that physics for collisions is conservation of momentum, it's an interaction. So the momentum will be conserved if in the interaction there are no forces which are external, which is the case here. So we write our old principle there. Total momentum will be conserved in an isolated system. We write the equation. This is the question we wrote before. But in this question, both the pellet and the block will move together. So we will not have two velocities after the collision. We will have only one velocity. So I wrote this next equation here, where I'm saying the momentum before, this is the momentum before the collision, the total momentum, will be equal to the momentum after. But in the momentum after, we have this common velocity here, which is the velocity after the collision for both objects together, means the pellet and the clay. I should write here something like a comma to emphasize is after. We leave this comma there. It's after the collision, okay? So we have the momentum before is equal to the momentum after, but we have a common velocity after the collision because both the pellet and the clay are moving together. Great. Let's solve the question now. Everything I write from here onwards in red will be about the pellet. Everything I write in blue will be about the clay. So I wrote the momentum of the pellet plus the momentum of the clay before will be equals to the momentum of the pellet and the clay together after. Please realize that I'm talking here about both objects moving together the same way I did here. Okay? These two terms are connected. Okay? These two terms are connected because we have the objects moving together after. Very important. So I will change now my momentum equations into mass and velocity, and this equation becomes this. And again, this is my common velocity that I wrote here before. Very important. Okay? We replace the values. Values are replaced. Red values are for the pellet. Blue values are for the clay. Common velocity is still here. I will solve for the common velocity value, solving the equation here, and the answer is 4.82, which is what they request in the question. Please stop the video now and take a moment to check this mathematics. Okay. Something interesting is understanding why the velocity of the group will be less than the velocity of the bullet. And to understand that, I put this video here. This video is about a bullet hitting a ballistic hell block. And in this video, you can see that the bullet is giving energy to the clay. This wave pattern you are seeing there is just the clay, the bullet passing, transferring energy to the clay. So the energy the clay is getting, which maybe can be translated into temperature of the clay, the internal energy of the clay will rise up. The energy the bullet is transferring to the clay it means that the kinetic energy of the bullet will be less. So at the end, the speed of the two objects moving together will be less. So something important to say here is that transfer of energy, conservation of energy is always related. And this video explained really well why. The collision will imply a transfer of energy between, in this case, the clay and the bullet. Of course, this video is not about clay, it's about ballistic gel, but I found it interesting to explain that these patterns, these black lines happening there like wave, are just the clay reacting to the transfer of energy of the bullet. So the energy being lost by the bullet, because it's given to the clay, implies the speed of the bullet, and the block moving with it will be less. Okay. The next question, B2, asks to calculate the average frictional force that the surface of the table exerts on the clay block while the clay block is moving. Don't forget, the clay block and the pellet are moving together. It's very important. So we will not use more physics for collisions. The collision already happened. For me now, from now onwards, I only have one object, which is a system of objects moving together, of the pellet and the clay. No more collision. The collision happens before. I say that because many students keep using momentum conservation when they don't need it. You only use momentum conservation for the collision, for the interaction, nowhere else. So if you're going to find a friction force, maybe you will not need to use conservation of momentum. You will maybe use momentum for the force, but not conservation of momentum at all. So I draw my free body diagram for my object, and I discover that the only force acting in the direction of the motion is friction force. It's this orange vector I draw here. So I will write the net force equation, which is the second Newton's law for constant mass, and I will have is net force is equal to mass times acceleration. If I apply this equation in the axis of the motion, which is the x-axis, I will discover that the only force acting is friction. Friction is pointing into my negative direction, so my equation will be this. My only force acting in the direction of the motion is that. And since I have the mass, if I find the acceleration, I will have my friction force. So I will consider that the acceleration is a constant acceleration because they are asking for the average friction force and they are not suggesting that the surface is changing in any way. So I can consider the acceleration to be a constant because the force of friction will be a constant since the surface is the same surface all way. So I will use kinematics for constant acceleration. This formula can be found in your formula booklet. I don't need the time value, so when I don't have the time value, this formula is useful. I will replace my values. My final speed will be 0. My initial speed is the ones I calculated before. The distance is given in the data, and I solve for acceleration, and my acceleration is negative 4.11, and it's negative because the acceleration is working for the block to get rest, so it's reducing the magnitude of the velocity. So I will replace this value in my formula. There it is. And then my friction force will be 0.24 newtons. Something very important to mention here is that in vectors, the negative signs are just the direction of the vector. So the value of the friction force here has a positive value, means we are calculating the magnitude. The direction, of course, will be negative, as we mentioned before. Okay? But it's always nice to write the negative signs to emphasize the direction of the vectors. It's very, very important. So that's part B2. So as you can see, in part B1, we use conservation of momentum. In part B2, we don't because the collision already happened. So, and I put the simulation there to emphasize that the net force acting is friction. So this is a spring being compressed by a bullet and a block. But if you check, the constant of the spring is only 1 newtons per meter, so it's a very, very low constant. So the only force acting there is this red arrow there that you see, which is the friction force. So the net force is friction force, and the friction is the force making the object to stop. Okay, that's a nice video that I found in internet. So the part C of the question is about parabolic motion. So I will ask you to stop the video now and read the part C question. Okay, so it's a very typical question about parabolic motion. It's a horizontal lunge. You have the clay block in the edge of the table. They give you a new value of a speed. It's very important. You will not use any more 4.8. You're going to use 4.3. And they give you the height of the table. And before going to the real question, let's do some physics about the parabolic motion. And I found this video in internet, thanks to Dr. Ángel Franco and Física con Ordenador for the simulation. So in this simulation, you can see that the trajectory of the object is a parabola, it's a parabolic motion. And you can see that the horizontal velocity vector, which is this horizontal vector, is never changing value. So the horizontal velocity is not changing, but the vertical velocity is increasing while the particle is falling down. This implies that if we analyze this motion from the horizontal and the vertical perspective, we will have that in the horizontal perspective we have constant velocity, which equation is this equation I'm circling here in blue, and the vertical velocity will change. So in the vertical direction, I will use free fall. These are the formulas for free fall that you can find in your formula booklet. If you replace u by 0, because the initial speed in the vertical direction here is 0, you have free fall. Okay? So I'm going to use this physics to solve this question. So the question says that if ignoring the air resistance, we have to calculate the horizontal distance traveled by the clay block before it strikes the ground. So, important. They are asking to calculate the horizontal distance. So if we remember what we did before, horizontal distance implies constant velocity. So this is the physics we're going to use, constant velocity formula, constant speed formula. We have the value of the horizontal velocity because it's given, is this 4.3 given here. But we need the time. We need a value of time to calculate our distance. I'm solving x from this equation and becomes this, and I need to find a time. So I remember that the time taken for the object, for the block to fall down this y direction will be exactly the same time taken by the block to reach this point. So the horizontal time and the vertical time, if such a thing can be said, will be the same. So the falling time, if we see this problem vertically, will be exactly the same horizontal time to reach the maximum value. So the maximum x value. So I will calculate the time using free fall. So I have my free fall formula here, and I solve this formula for t. Some students find solving this algebra a little bit tricky. So this square root is because the t has a power of 2 here. So if you check your algebra, you will discover that this formula solving for t becomes this. And I have the y value, which is 0.85, it's given. So I replace my values there. My gravity is 9.81, my y value is 0.85, and my time is now 0.416 seconds. So this is the time taken to fall down, which is exactly the time taken to go to cover the x direction. I did a mistake here. This arrow should not go from this base, should go from the place where the clay is located. Well, the x should go from here. This should be the x. Sorry for the mistake. So I will replace my time value in my equation. So that's the replacement of the time value in the equation, and this is the value of the distance. There is an extra question here where they ask that to draw the trajectory of the clay if air resistance is now present. So what will happen is that the mechanical energy of the object will be less because some energy is being lost into the friction with the air, into the air resistance. So the object will have the same trajectory, but will hit before, because some mechanical energy is being transferred to the air due to the air resistance. Okay, I hope you found the video useful, and see you in the next video. Thank you.